Yes. Okay, we're recording now. Hello, hello. We will start on induction today. Let me share the screen with you. Okay. So here's so induction chapters 8.4, 8.5. Induction is a technique for proving theorems parameterized by integers. Okay, so for example, something from the last week. You have, let me get a better pointer. You have a summation, okay, a summation expression, which is a sum from j equal 1 to n of, what are you summing? Just j itself. So it's a sequence, you're summing over a sequence, and a sequence is like a very simple sequence. It's an identity. So jth element of the sequence is just j itself, okay? But it is a sequence. Okay, so this is, it is an arithmetic sequence, right? Because a difference between j and j plus first element is constant, is 1. These guys are in our, it's an arithmetic sequence. It's 1, 2, 3, 4, 5, 6, right? This is an arithmetic sequence with the starts at 1 and has an offset 1 that it just gets added. And the question is, what's the summation over such a sequence up to n? And the claim is that the closed form for this summation is this right-hand side. Okay, we had it last week, but we didn't prove it. We just claimed it. Okay. This is a statement about an integer n. The statement about an integer n here is that the sum of integers from 1 to n is equal to n squared plus n over 2. It's a statement about n. It's a predicate. This predicate is true, maybe, about some n's, maybe it's false about some n's. This theorem claims that this predicate is true for all integers n from 1 on. Okay, so in what sense it's parameterized by n? Because this is some predicate involving n, and we can call this predicate, for example, p of n. And what's the predicate? This is the predicate in this case. It's that the sum of first n positive integers equals n times n plus 1 over 2. In other words, this stuff in the box. Okay. Now, how does induction help us prove such statements? Let's say that you have some statement parameterized by integer to prove. The example is from last slide, right? Like from the previous slide. Think of this predicate, p of n, to be what we claimed last slide, namely existing. Okay, but there's just an example. You might have some other statements about integers, and there's just an example of such a statement. And the theorem is that your statement about integer n, for example, this one, holds for all n from 1 on, okay? All n greater or equal to 1. Now, a proof of this, of any such statement, there's many ways to prove statements, right? But one type of proof, one we will be teaching today, is proof by induction. And the proof by induction contains 2 sub-proofs. The first one is that you're proving directly that the predicate is true about the first integer in this range where the predicate should, where the claim is that the predicate holds in the range that starts at 1 and goes to infinity. So the base case is that you're proving it directly about the integer that is beginning of your series. In this case, it's 1. The inductive step of the proof is a proof of an implication. the proof of the following implication. The implication is that for any integer k greater than this initial threshold, the following statement is true. The statement is in the form of implication. If predicate p holds about k, then it holds about k plus 1. Okay. So typically, of course, this inductive step is the whole logic of the inductive proof, and it's usually the harder part. The base case is a direct proof that the predicate holds for one particular integer, and the inductive step is a proof of an implication that if a statement holds about integer k, then it holds about k plus 1, regardless of what k is, except that it has to hold for any k greater or equal to 1. Okay, so in other words, what you are proving in the inductive step is the following implication. For every k, you have to prove this implication. If k is greater or equal to 1 and this predicate holds about it, then the same predicate holds about this integer incremented by 1. Okay? Now, why these two proofs, the proof that the base case holds and the proof that this implication holds, why should they together imply what we wanted, which is that this predicate holds about every integer greater or equal to 1? Well, let me show you, sort of try to convince you that this is indeed suffices to conclude that with the following reason. So note, first of all, by the base case, so I will argue that this is indeed implied by these two. So let's first ask, okay, is it true that P, have we proven that P holds on about n equal 1? Yes, of course, in this part. Now, have we proven that P holds about 2? Well, in this part, we have proven that for any k greater than 1, pk implies pk plus 1. So instantiate this statement with k equal 1. Then in particular, it means that p of 1 implies p of 2. But we already know that p of 1 is true, right? We proved it in the base case. So the only world in which p of 1 is true and the implication that p of 1 implies p2 is also true is a world where p2 is true. Okay, it could not be that this is true and this implication is true, but p2 doesn't hold. Right? If p2 doesn't hold, then either this is false or this implication is not true. But you just proved that the base case holds and the implication is true for any k. So you can conclude that p holds about 2, and of course, just recurse. So instantiate this with k equal 2. This means in particular that p of 2 implies p of 3. So this thing. And now we already know that p of 2 is true. So now we can conclude that p of 3 is 3, and so forth and so forth, right? So by induction implies a proof for any n, because it's like a little engine. The engine says that first of all, in the base case, I'm turning one index as proven. And I have this little recursive engine that says that if this is proven about k, then it's going to be proven about k plus 1. And now I just apply this engine recursively. If proven about 1, so therefore proven about 2, proven about 2, then therefore proven about 3, proven about 3, proven about 4, and so forth, right? It will eventually get to any integer you like. Are you concerned whether it's true for n equal million? Well, run this recursive loop million times, and it will imply that p holds about million, right? N equal million. So there's a philosophical thing here, because it's some mathematicians sort of pose, okay, what would mathematics look like if we disallowed proof by induction because these proofs prove the statement, but they kind of create like an infinite size proof for every n, or like that the size of the proof depends on the n, because if n is large, I have as many of these implications I have to do as n. But this is a philosophical thing that we shouldn't concern ourselves with now, right? Like almost everybody says, induction clearly shows that this is true for any n, because I can do this logic n times, regardless of what n is. Okay. So some examples, right? Let's say that this is our what we wanted, right? Like this was the predicate that we started with. Now, recall, inductive proof, you have to show the base case. First of all, what's the predicate here? Okay, the predicate is this statement. Okay, that's the predicate on n. And the theorem is in the form that this predicate holds for all n greater or equal to 1. So this is the blueprint for induction. If the statement is of this type, and it is, then the inductive proof for it will consist of two parts. The base case, proof directly that this predicate holds about n equal 1. Secondly, the inductive proof that if this predicate holds about argument k, then it holds about argument k plus 1. Okay, there is a change of variable here. I can just as well express this that for all n, Pn implies Pn plus 1. And the only reason why I prefer to use a separate variable than this one is so that not to get lost and not to make error as I go from one variable to another. So I'll show this to you on the page, what kind of error you can make, okay? For this particular predicate and for these types of predicates, it is convenient to think of this as, okay, here is some function of n. Let's call this the left-hand side function. This function for every n, to every n assigns this summation. And this is also some function of n. Let's call it the right-hand side function. For every n, it assigns n times n plus 1 over 2. And the predicate is that the left-hand side function and the right-hand side function always have the same output, same value. So what's the base case? Well, it's that this predicate is true for 1. In other words, that this expression for n equal 1 is equal to this expression for n equal 1. In other words, this. Well, this is easy to prove directly, right? Left-hand side is the summation from j equal 1 to 1 over j. What this is, it's actually something very simple. It's just 1. Yes, because the summation goes from 1 to 1. And the summation is over the same thing as the index of the summation. And what's the right-hand side expression for n equal 1? Where it's 1 times 1 plus 1 over 2. So that's 2 over 2. That's 1, and you're done. Indeed, you have just proven that left-hand side for n equal 1 is the same as the right-hand side for n equal 1. Okay, so far so good. So now let's do the inductive step for this predicate. Again, we have to show that for any k, if this thing is true for n equal k, then this thing is also true for n equal k plus 1. Okay, so this is the predicate on n, and we have to prove this thing. Which one is it here? Okay, so I take a pause, I turn on the chat, and you make votes. Which of these fits this blueprint for this predicate? This is a function of n. and I need to say which one of these expresses that this thing, when applied for n equal k, implies the same thing, but for n equal k plus 1. It is this one, right? Because this is this predicate with n equal k. Okay, it's just a copy. And the right-hand side is the same predicate, but when n instantiated is k plus 1, right? And this is also why I am using a different, well, it's healthier to run your, to sort of write down what this implication is using some other variables than n. Why? Because, if I used n here, then of course writing this down would be very simple. It's just a copy of this. But I claim that writing this down with n replaced by k is just as simple. But writing this down when instead of n you have n plus 1 is going to basically, it's more error prone than if you replace n with k plus 1, because replacing n with n plus 1, you can see how you can make a mistake here. You have to be careful. Now this becomes n plus 1 and this becomes n plus 2. If you have more complicated expressions where n appears many times, replacing n with n plus 1 in your head, this is easier because there's a separation between n here and a k here, right? That you don't have to do this change of variable. It's just that it's healthier to use a different variable. It's less error prone. Okay, so this is the one, indeed. Okay, so let's prove it. Okay, so I guess at this point, okay, so this is what I need to prove in the inductive step. So let me write this down on my little thingy here. So you start this, is it for a while, for every k equal 1, if okay, I will just go to the document camera now and to pen. Okay. 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 So the proof is that this is what I want to prove. For every k equal from 1 on, if the summation from j1 to k over j is equal to k plus 1 over 2, then a summation from j equal 1 to k plus 1 over j is equal to k plus 1 times k plus 2 over 2. Okay, and this predicate is, by the way, p of k. Okay, whereas this thing is a p of k plus 1, and therefore the whole thing has a form for every k from 1 on. If p holds on k, then p holds on k plus 1. How do I prove this? Okay, here is the convenient one. This is our goal. So this is the goal that we want to prove. And this is our assumption. And this assumption has a special name. It's called inductive hypothesis. Inductive hypothesis. I think I missaid it, hypothesis. Okay. So under this hypothesis, I want to prove this. So here's how it's now. How can I prove this using this as a hypothesis? Well, here's one way. Which part of this equation is sort of most similar? Well, this summation has a very nice recursive relation to this summation. They are related by recurrence relation. What is that? It's a very easy relation. This summation from J1 over J can be expressed very easily in terms of that summation. Why? I just take that summation and I add one more element in the sum, namely the last one, which would be k plus 1, right? Because I'm summing over j's and I'm missing the k plus 1, so I'm adding it. So this is obviously true, right? This is by, this is the recurrence relation that I just mentioned. It's like written here, right? This summation is the previous one plus the new element. Okay, and now you can use, but hey, now it's very easy to use the inductive hypothesis. By the inductive hypothesis, you can assume that this expression is equal to this. So you can replace it by k plus 1 over 2. And you should not forget that there is this part hanging on. So you have to copy it. And how did you make it? Write it down by inductive assumption. Okay, or hypothesis, aka hypothesis. Okay. Please, when you write an inductive proof, you mention where exactly you're using inductive hypothesis. This is the equation that is implied by this assumption. Okay, so write it down because sometimes it's very clear, sometimes it's less so. Okay. Okay, what now? What are we trying to do? We're trying to argue that this summation is equal to this expression. Well, we have already shown that this summation is equal to this expression. But maybe we can take this expression and show that it's this one by some simple arithmetic manipulations. Indeed, they are already very close. What arithmetic manipulation would you do? Okay, so let's first put these guys into a way so that they're apples and apples, right? Okay, so now you see that this is k plus 1 plus 2 k plus 1 over 2. Okay, and now, well, it's the same term, right? So this is now k and 2 of this term, so it's k plus 2, k plus 1 over 2, and I'm done. Okay. Questions? And I'm done, right? Because I have shown that this holds, that the left-hand side equals right-hand side. And by this series of changes, I have just shown that this left-hand side equals this, right? So I'm done. And I have shown this under the assumption that this is true. Where did I use this assumption? Right here, by replacing this guy with this guy. Okay. Now, many of the proofs in the book will have this form because there is some recursively defined object. It's a summation. Why is it recursively defined? Implicitly, it is, because this is the recursive definition of what a sum is. Sum over 1 plus, whatever plus 1 is the sum to whatever plus that missing one. Yeah, this is an implicit recursive definition of a summation. Okay, so many things that we'll ask you to prove will have that structure. Are we good? So shall we? I'll come back to the. Somebody else, is this how we should write our solution on the exam? Yes, of course. I believe, my proofs are like the cleanest, most aesthetic ways of expressing an inductive proof. Joking aside, there is many ways you can do this, right? But okay, this I hope is the clear one. And the style of the proof will change as in order to fit what it is that you're proving, right? So let's see more examples, so you can generalize the structure. But the part that is always going to happen is that at some point the inductive hypothesis, you will kick in the inductive hypothesis to get you through some some step. Okay, let me go back to the presentation. Okay, so this proof we have just done. Okay, so here is another example. So this one I have typed here. So let's say you want to prove. Now, let's change it, not an equality, but inequality. So a theorem is that n factorial is greater strictly than n squared. And the theorem is that that is true for all n from 4 onward. Okay, so what's your predicate? This is the predicate. Okay, so the predicate is here. It's this statement. It's a predicate on n. Okay, and what else? So that part sort of hasn't changed. It is some. Hold on. Hold on a second. Sorry. Let me maybe know whether my face is particularly better than this piece of paper, but maybe it's a little bit. Okay, so it is a predicate on n. Okay, it's a predicate in the form of inequality rather than equality, but other than that, well, it's some predicate on n. What has substantially changed is that now this theorem says that this predicate holds about n, not starting from 1, but starting from some other constant. In this case, this constant is equal to 4. Okay, so what would the inductive proof look? Well, the form we gave just a few slides again is actually not the most general. If you generalize it so that this theorem is a predicate holds from n starting at some constant c, then the base case would be prove that the predicate holds about c, and the inductive that if the predicate, you have to prove that the following implication: predicate holding on k implies predicate holding on k plus 1. That's the same, but you have to prove it for all k at least c. Okay, so right, because first you want this statement and this statement to first of all imply that p holds for like c plus 1. So, well, it would imply it if this is true for k equals c. So k equals c is the first one for which this implication has to hold, so that this thing and this thing can together imply that p holds about c plus 1. And because it holds for k greater or equal to c, so in particular it will also hold for c plus 1, and therefore this will imply that p c plus 1 implies p c plus 2, and that p c plus 2 implies p c plus 3, and so on, right? So the same logic. The only thing that changed is the constant came in here, it modified the base case, and it came in here again to tell you implication has to hold for all arguments starting from that constant. Okay, so What is the base case then? Well, it's to prove this for n equal 4. Okay, so what do we have? That 4 factorial is at least 4 square. So let's test. 4 factorial is 1 times 2 times 3 times 4, which is 6 times 4, 24. 4 square is 16, and it's true, right? 24 is larger than 16. Why did I start at 4? Because for 3 is not true. 3 factorial is 6, 3 square is 9. So this is just false for n equal 3. Let's see that it's true for all n greater. How do we see? Well, we have to prove this. So now on to the inductive step. So in an inductive step, we have to assume, well, we have to prove the following. If the predicate is true about k, in other words, if k factorial is at least k square, is greater than k square, then the same thing is true about k plus 1. In other words, k plus 1 factorial is greater than k plus 1 square. So that's what we have. Assuming for any k greater or equal to 4, that k factorial is greater than k square, we have to prove that k plus 1 factorial is greater than k plus 1 square. Okay? And it has to work for any k greater or equal to 4. Whatever arguments we use, have to work for any k in this range. Okay, so now which of this part is sort of similar? Okay, I guess they all, this is similar to that in some sense, right? But the left-hand sides are related by a recursive relation. This object, it's a recursively defined function. What is a k factorial? What is a k plus 1 factorial? It is recursively defined as k factorial times k plus 1, right? So factorial has a natural recursive definition. Factorial of 1 is 1. What is factorial about n plus 1? Well, it's a factorial of n multiplied by n plus 1, right? That's how I define factorial, right? In other words, k plus 1 factorial is k plus 1 times k minus 1, da, da, da. I group all these things as k factorial, and I get, I don't know what happened here, I get this, right? So this is just a recursive definition of a factorial, and if you don't remember recursive definition, it doesn't matter. You see it right here, right? So it's sort of easy to observe. And now I can use this, right? I expressed left-hand side of this expression as some function of this thing. So perhaps let's try to use inductive hypothesis at this point to conclude this, right? K plus 1 times k factorial must be greater than k plus 1 times k squared by inductive hypothesis. Why can we? Because k is greater or equal to 4 here. And, that's what we assume about k. Okay. Oh no, my thing says that connection is unstable, but hopefully it's a temporary issue. Now the rest is arithmetics, okay? Because we already used this link between this thing and this thing. We already used the inductive hypothesis. So now we have this expression. And now we should just, by arithmetics, somehow see, hopefully it is true, that this expression here is greater or equal to this one. Because if it is true, then we'll be done. We will show that k plus 1 factorial is bounded by from below by k plus 1 squared. If we show that this thing is greater or equal to that one, right? And now if you see what is k plus 1 times k squared, I mean, how can you show this? In many ways you can show this, that this is greater or equal to that. For example, if you show that k square is at least k plus 1, then this would be greater or equal to k plus 1 square, right? And k square is greater or equal to k plus 1 for, k from here, right? So we're just now searching for some bunch of arithmetic changes that will exemplify that this thing is greater or equal to that thing. There is many such changes. There is now it's arbitrary. It's like you can prove it one way, I can prove it another, a third person can prove it in yet another way. There is many ways to get there. This is particular way, okay? So in particular, in order to show that this thing is at least that, I can change this by k times k, and just write this, okay? Well, you know that k is greater or equal to 4, so in particular, k is greater or equal to 2. Okay, it's true. And now 2k is, well, that's k plus k. And that, of course, k plus k is greater or equal than k plus 1, because k is greater or equal to 1, because k is greater or equal to 4. So if k is at least 4, then it's at least 1. Just like we used here, that k is at least 2. Yes? If k is at least 4, then it's at least 3, and it's also at least 2, and it's also at least 1, and it's also at least 0, and anything smaller than 4. And this is k squared. Okay? So, but this particular derivation might appear unnatural to you. Well, if you scrutinize it, it just proves, it just proves that this thing is at least this thing. You can prove it in many ways. Okay, this is just particular way. There's nothing fixed in stone here. Okay, a lot of people are hung up on a particular derivation here, and they say like, oh, why do I have to use this derivation? And I say, you don't have to. You pick your own derivation, like whatever you want. Just show somehow that this thing is at least this thing. Okay. Okay. Yeah. In step 6, we used that. No. Well, in this equality is just that 2k is the same as k plus k. And in this inequality is that k is at least 1. And in this inequality that k is at least 2. What changed into equal sign? Sorry, you mean here? It didn't change, it's true. 2k is equal to k plus k. Okay. But you could also write greater or equal. It's also true. Yeah. Okay. The key step is 3. Well, yes. This is the moment when you use the inductive hypothesis. So this is like this jump is the it's the shot of a gun here, right? Because truly we have no idea, like, is k factorial greater than k squared? Okay, maybe it is, maybe it's not. We assume that it is, and that's what we used here. You see, inside of the inductive proof, you don't really care whether the assumption is true. It is given you, because all you have to do is that the assumption, if assumed, it implies what you need. I mean, of course, it would help, probably if the assumption looks completely insane, then perhaps you're doing something wrong. Perhaps it was a wrong assumption to use, right? But in some sense, you don't care if this thing is true, because what you're doing is the proof of an implication that if it was true, then something else is true. And that you succeeded in proving. Indeed, this thing is at least that if k square is at least k square, if k factorial is at least k square, because everything else here was the fundamental arithmetic, so there could be no doubts about it. This part is just based on the inductive hypothesis. But so we don't know if it's true, and we don't care. We're only showing that if it holds, then this holds. And that is enough by the principle of induction. The principle of induction says that if you show this implication from that this implication holds for any k from greater or equal to c, then that suffices for this predicate that you have proven that this predicate must hold for all integers greater or equal to c. Okay, sorry, if you prove this implication and if the base case was proven true. From step 2 to 3, is it just taking k square and multiplying? From 2 to 3. From 2 to 3, the only thing that happens is that I'm using the inductive hypothesis. Yeah, because this is some stuff that this is multiplied with, so therefore I carry that stuff. By the way, I used also that stuff is positive, right? So if A is greater than B, then A multiplied by something is greater than B multiplied by that something, only if that something is a positive. And it is, because k is greater or equal to 4. Okay. Okay. I'm reading somebody's post and I'm trying to see if I answered it. I think so. I'm not sure. Yes, I'm multiplying each side by k plus 1. Okay. Yes, and you can do this because k plus 1 is positive. If it was in equality, you don't care, but this is inequality. So it only implies that this multiplied by k plus 1 is greater than this multiplied by k plus 1 if k plus 1 is positive, but it is. Okay. Here is some other thing to prove by induction. So it's a different type of statements. Okay, like there is the universe is full of statements which are not so easy to prove directly, but you can prove them by induction. Here is like another class of things that fall into this, into this super class. Let's say I want to show that some arithmetic expressions like this are always divisible by 12. Okay. You can test it for small n. So when, but it's actually true for any integer. It's a little funny to see because this is, power of 5 and you subtract 1. So, well, this is always an odd number and you subtract 1, so you get an even. Okay, so it's divisible by 2, but why is it divisible by 12? That's a little harder to see directly. But actually, it's very easy to show by induction. But let's rework this statement a little bit. To say that some integer, let's call this integer here m, that 12 divides this integer. That's basically to say that this integer is a multiple of 12. In other words, that there exists some integer, j, such that 12 times j would equal to this thing. Okay, that's the same thing to say. That's to say that 12 evenly divides such an integer. So, So we have to prove by induction this. So the inductive step will be that for any positive k, if 12 evenly divides this expression, then 12 also evenly divides this one. So which of these statements is that? So the inductive hypothesis is this one, that 5 to the 2k plus is evenly divided by 12. So that means that 12 times something is 5 to the 2k minus 1. But if you move 1 to the other side, then you will get that 12 times something plus 1 is equal to this. So people are silent, but it's this one, right? That's the same as to say that 5 to the 2k minus 1 is 12 times something, which is this statement, okay? This statement is the same as this one. Okay, now what about this part, right? Okay, so let me switch to the so this is what we want to show, but then I will like switch off these slides and go back to my little piece of paper to do this. And okay, so focus on. Okay, so the statement was again, for every k at least 1, if 5 to the 2k can be expressed as 12j plus 1 for some j, and this, by the way, was our predicate p of k. Okay, that something holds about k, and this on the previous slide is described as which is the same as to say that 5 to k minus 1 is divisible by 12. Okay, that's the same statement as this. So if this holds, then 5 to the 2k plus 2k plus 1 is, well, okay, so what's our predicate? The predicate should be p of k plus 1. What is it directly? It is that 5 to k plus 1 minus 1 is divisible by 12, right? So how do I express it in this kind of form? Well, if this is divisible by 12, which means that this is 12 times something, so therefore this is 12 times something plus 1. Okay, so that's what I will write. It's 12j prime plus 1 for some j prime. And I don't care what j prime is, because it just has to be some integer. Okay, so that's what I want to prove. You know what? I guess I never proved the base case. So first of all, base case, the missing one. The base case is that I have to prove it for 1, right? So in other words, that 5 to this is 12 times something plus 1 for some j. But that's true because this is 25. So therefore, this is indeed 12 times 2 plus 1. So therefore, P1 holds. Okay, and that's not supposed to be here because I'm supposed to prove the inductive case. This was just a base case missing, right? Okay, so let's go back to, avoid the base case. This somehow should be before. And let's do the inductive case, right? Inductive step proof. Okay, So, well, this is what we need to prove, and this is our inductive hypothesis. Well, let's try to use our old style thing and try to maybe express this as some function of that, then use the inductive hypothesis to replace that by 12 times something plus 1, and hopefully this will let us express this thing as 12 times something. Okay, let's try this. So we have 5 to the k plus 1, and let's work it so that we can see, well, what is this? You had that chapter to read about functions, in particular about exponentiations and logarithms. So you should know, okay, so, well, this is just a multiplication, that this is 2k plus 2. Okay, well, but what is the exponent? You know, when I add in the exponents, this is the same as 5 to the k times 5 to the 2, right? Because the base to x times base to y is the same as base to x plus y, right? So this is the general law that I just used here. Okay, so okay, I do see my 5 to the k now. Okay, so let's use an inductive hypothesis now. By inductive hypothesis, I can rewrite this thing as 12j plus 1 times 5 to the 2, okay, for some j. The inductive hypothesis tells me that this j exists, that no matter what k was, if it was in this, you know, I can assume that this is true. Okay, so I just did. Okay, so now the rest is arithmetics, because let's write what this is, right? So this is 12j plus 1 times 25. Okay, and well, I guess let's multiply this stuff. Okay, well, so this is the same as 12 times 25 times j plus 25. Okay, so this is the same as 12 times 25j plus 12 times 2 plus 1. So this is the same as 12 times 25j plus 2 plus 1. So therefore, this is the same as 12 times j prime for some j prime plus 1, specifically for j prime equal 25j plus 2. But I really don't care what the j prime is. It just has to exist, and it does. Yeah. Okay, so therefore, pk plus 1 holds, assuming that pk. Oh, sorry. Oh goodness, don't see anything. Okay, so you know what? When this happens, please just speak up, because I cannot. Sorry, people wrote, right? And thank you for writing. The thing is that I don't look at the chat when I'm writing. So please, next time, just say that you ran out, you know. Okay, sorry, this is an interface issue. I don't see what you see. You don't see what I see. Okay. Assuming PK holds. Okay, sorry. So I don't know at what point you couldn't follow. Maybe. Okay. So I'm like letting you catch up. I'm not sure, you know, whether a lot of stuff I said you had to take for granted or not so much. Okay. Shall I repeat some of the stuff that I just said or not? J prime 25 J plus 2. Okay, well, yeah, so that's not much. Okay. Thank you. It's in some sense, you know, what is happening here, right, is that when you look at this statement, that a power of 5 to some positive power is always 1 plus some multiple of 12. It appears like, how do I show this directly? But turns out that with induction, it's basically very simple. And again, you know, when I made this change here, when I could express 5 to the 2k, 5 to the 2k as 12 times something plus 1, I really don't know whether it's true, right? But within this proof, I don't care whether it's true. I am given this as an assumption, and under that assumption, I'm proving that this is true. Okay, that if 5 to the 2k is expressible as multiple of 12 plus 1, then 5 to the 2k plus 1 is also expressible as multiple of 12 plus 1. And it's a conditional statement. And you can see that in this proof, I don't really, you know, I assume it's true. I have no idea how it was proven. I just can assume that this is true. But the power of induction means that indeed this base case thing, very simple, and this inductive reasoning, which in the end is fairly simple too, does imply that this predicate holds for every k, for every integer k. So I think that, you know, many of these examples do show like really amazing power of this methodology. Okay, and I see that you guys are helping one another, like what happened, you know, why certain equation holds or not. So thank you for that. Let's do one more. So let me show my my face and then come back to this. Okay, so this is what we were arguing. Okay, here is another one. Wait a second, somebody said sick just when I talked about my face. How do you mean that? No. All right. So let's prove the following. Okay. So let's prove the following. Here is a recursively defined. Here is a recurrence relation. It's a sequence defined through recurrence relation, namely the first element of the sequence is -3, and for all n greater or equal to 1, the nth element of the sequence is defined as 2 times the previous one plus n squared. Is this recurrence relation successful? In other words, does it really define a sequence? Well, G0 is defined. Let's see if G1 is. Well, G1 is defined in terms of G0, which is defined, plus some arithmetic expression. Okay. Yes, and so G2 will be defined as 2 times G1, which is defined in the previous step, plus some arithmetic expression. So this works. It does define some sequence. We can write out a bunch of elements of this sequence. And here's a claim that this little code, in fact, defines this sequence. So the closed form expression for Gn, for any n, is this expression. Okay? It's not very obvious why that little recursive code ends up defining this particular sequence. Towards the end of this chapter, we'll see how to derive these. Why do we care about deriving? Because, as we said last time, recurrence relations are natural ways to describe like what happens in some algorithm, or some biological system, or some other whatever network system that you're trying to describe. And it is helpful to know that there are methods for how to go from this to, like, can you estimate what this is for any n? Does it behave like a quadratic function? Does it behave like an exponential function? And it does. Okay. So let's see how to prove this. Okay, let me go to to a piece of paper again. So by the way, the slides are online, right? So you can also, sitting at home when you watch the stuff, you can just maybe download these slides before a lecture, and this will help you synchronize, right? So but here is, but you can download them also right now very quickly. So this was the recursively defined sequence. G0 was -3, and Gn was 2, Gn -1, plus n squared. And that was for all n at least 1, right? So here is our little recurrence relation defining a sequence G0, G1, right? And our claim is that for every n, Gn has the following closed formula: 3 times 2 to the n minus n squared minus 4n minus 6. Okay. So let's see if this is true. I will denote this as a f of n. Okay. So this expression I will denote f of n, so that not to get lost in arguments, what I'm arguing. Okay, so let's see, what does base case looks like? What do we have to prove in the base case? Well, okay, so I didn't write, let's write it here. For every n greater or equal to 0, okay? Yes, because my starting point is 0. So I want this closed form expression to express all values of the sequence starting from the first one. Okay. So what's the base case? Is that the base case is that G0 is f of 0. Okay, that the first element of the sequence is expressed by this formula, instantiated an argument 0. So let's see. Okay. So that's a claim in the claim here is that this is what we have to prove in the base case. Okay, so now what is f of 0? It's 3, 2 to the 0 minus 0 squared minus 4 times 0 minus 6. So this is, what is 2 to the 0? That's 1. So it's 3 times 1. All of this drops out, minus 6. So it's 3 minus 6, so it's minus 3. Done. Right? Because we have just proven f of 0 is minus 3. and G0 is also -3. So they are equal. Okay. Inductive step. Inductive step. What are we showing? Okay, we need to show that for every k greater or equal to 0, if gk is equal to f of k, right? So what's the predicate here? So I would denote it f of n. The predicate is p of n. Predicate is that the nth element in sequence is equal to the f function at argument n. Okay, that's your predicate. That's the predicate here. Okay, that we are proving for all n. Okay, so this is the predicate at point k, and if this predicate holds at point k, then the same predicate holds at point k plus 1. In other words, that the k plus first element in the sequence is equal to the f at k plus 1. Right? So this part is p of k, and this part is p of k plus 1. Okay? You don't have to make all this stuff in your proofs, right? Like this is kind of for educational purposes. I'm denoting f, here is the hypothesis, here is the thing, here is the predicate. You don't have to define a predicate unless we ask you. We say, okay, state the predicate. Unless, other than that, if you don't state the predicate, we don't read. Okay, then yes, state the predicate. Okay, so this is what we're proving. Okay, is there something recursive here? Is there some part of this that can be linked to that? And yes, I mean, explicitly, the whole sequence is defined by a recurrence relation. So therefore, this guy is explicitly linked to this guy by this recurrence relation. So let's follow that. Gk plus 1 is equal to 2 times g. Well, so now you have to be careful changing variables, right? This recursive definition in terms of n, and it defines nth element as 2 times gn minus 1. What is n here? N is k plus 1. So g at index k plus 1, this is my n, k plus 1, is equal to 2 times g n minus 1. N minus 1 is k. This is n minus 1. So 2 times g to k plus, and n was k plus 1. So it's k plus 1 square. It is a change variable that you have to do. Okay. There is no way that a statement like this can be convenient both for this predicate and for this one. So regardless whether I state, you see, if I state it this way, it's most convenient to use here, right? But if you have to be comfortable changing variables. I can, okay. Let's do this one in one version, and then maybe just for the heck of it, let's see how this would look if we set up these variables slightly differently. Okay, so this is how can I conclude this? By the recurrence relation of what the Gn is. Okay, instance for n equal k plus 1. That's why I could write this. Okay, and now, of course, what I will do is that I will use the inductive hypothesis, right? So by inductive hypothesis, this is equal to 2 times f of k. plus k plus 1. And this is by inductive hypothesis. Right? I can replace gk by f of k. And now what is f of k? It's this arithmetic expression. So let's see. Sorry, minus n squared minus, sorry, it's k, not n. So what is f of k? Is 3 to the k minus k squared minus 4k minus 6. And let's not forget this part, plus k plus 1 squared. Okay, now I somehow have to go from here to here, right? Because my whole goal was to, under this assumption, prove that gk plus 1 is f of k plus 1. I have gk plus 1 here, and by a series of answers, I have managed to replace it by this arithmetic expression. So let's see if it does equal to this one. Okay, then perhaps I should see, well, what is this expression? Okay, but so that is like now an interruption in the proof. But what is fk plus 1? Fk plus 1 is 3 to 2 k plus 1 minus k plus 1 square minus 4 k plus 1 minus 6. So the goal is, we would be done if this whole thing, if we show that this thing is equal to this thing. Let's give them names. I'm gonna call it star and double star. And so, proof will follow if you show that the star expression in the star box is equal to the expression in the double star box. Yes? Because if this whole arithmetic stuff is equal to this arithmetic expression, then you're done, because this means that whatever this is indeed equal to fk plus 1, which was what you were supposed to show. And because this is some arithmetic expression, and so is this one, there is a million ways of showing that these two arithmetic expressions are the same. Okay, so you're sort of from now on, it's the wilderness starts, because like I can do it one way, you can do it some other way. There's many ways to do this. So let's see. Okay, the star expression is equal to 2. So let's group these elements, right? This would be a convenient way. Let's put 2 inside of here. So now this part looks very much like that one. Now let's multiply this further. So it's 2k squared. Further, it's minus 8k. 2 minus 6 is minus 12. And now I have this thing. Maybe I should skip it because I have the same thing here. But unfortunately, here it appears with a plus, and here it appears with a minus. So maybe I should just see what. Well, I guess let's just evaluate it and see. So this is k squared plus 2k plus 1. So it's 3k plus 1 minus, let's just group them, minus 2k squared, k squared, so minus k squared, 8k minus 8k, 2k, so it's minus 6k, minus 12 plus 1, so it's minus 11. Okay, so you know what? Let me just evaluate this thing in a similar fashion. So this thing is okay. The first part, I'm glad it's directly the same. And let's see this part. Okay, so k plus 1 squared. So it's minus k squared plus 2k plus 1 minus 4k minus 4 minus 6. Okay, so let's have so I keep this guy, of course, because it's already the same. Okay, let's group the terms. So I have minus 2k squared here. Minus k squared minus 2k minus 6k, so that's minus 6k, minus 1, minus 4, minus 6, so it's minus 11. So indeed, this is the same as this. So indeed, this shows that these two expressions are the same. So therefore, gk plus 1 is indeed the same as fk plus 1. Okay. This is one way to show that this expression is equal to fk plus 1. These are complicated arithmetic expressions, so you can go any way you want as long as it is clear. You know, my way of doing it, you know, it's clear for me. Might not be clearest for everyone. There might be a more concise and proof, right? In particular, if you just if you evaluate what fk plus 1 is, so you know your target, then you can rearrange. You know that, okay, so this you should replace by, you know, by this, right? And then you should just mold this so that you end up with this expression, okay? Which, and by mold, I don't mean cheat, I mean show the exact changes so that, like, whatever this is, indeed, in the end, it looks like this. If you know your target, you can manipulate these expressions until, you know, you either show that it hits this target or you can't, and that means you might have some, you know, you made some mistakes that you have to correct. Okay. The you know, the more you do this, the more you see a pattern, and then, but you know, there's some parts that are fundamental. An inductive hypothesis has to kick in. There is a recurrence. There is some recursive relation between, you know, some object about which you're trying to prove something and the one that you can assume, that you can already assume something is true about that one in the inductive hypothesis. This part will reoccur in inductive proofs, but some parts are sort of, you know, basically freestyle. You know, it's there is no pattern. There is some arithmetic expression that you need to show is equal to some other arithmetic expression. If you haven't made any mistakes, then you can show it. If there is some issue, this is perhaps because you have made some mistakes. You know, perhaps you forgot a term. Perhaps you have carried, you know, when you instantiated this formula, perhaps, you know, you forgot this term, or perhaps you have used, you know, somehow, you know, got messed up with that this being k plus 1, so therefore now this becomes k, but this one still stays k plus 1, right? There is unfortunately plenty of places where you might, you know, that you might make a mistake, but just, you know, try not to panic. Just verify and you know, backtrack, fix, and go on. Okay. Do you have any questions?
For the quiz, we still test until 8.6, right?
Wait, say this again. For the first test, which is in a week, are you asking about the test next Thursday?
Yes. So is also continued like test until 8.6?
Sorry, I don't hear what you're saying. The
He's
test
trying
is
to
during
ask
the
what.
lecture, so it goes from 3:30 to 4:50. Is that what you're asking?
Yeah, we're just trying to ask what sections does the test go over?
Oh, no. It will 8.6 is the, I don't have the book in front of me. What's 8.6? Okay, I'm gonna check because I don't want to make a mistake. The test will end on stuff we do today, which is induction, but it will not cover strong induction, which will be next week. And let me just check. Strong induction is 8.6. So no, so the test will end at 8.5. And the homework also does stuff until 8.5. So, okay, yeah, strong induction is postponed till next one. I know that at the beginning on the syllabus, I thought I will we will get to strong induction before test one, but we did not. And yeah, we'll post some practice exam, some practice test tomorrow. But you know, don't think that the practice thing is all that you have to do. What you have to do is the homework, and what you have to do is the exercises from the book. The practice test we'll post will be some selection of problems. It's not necessarily the selection that will be like, you know, on the test we'll have another selection of problems. Okay. All right. Okay, everyone. So you know, work on the stuff and keep us in